All right, guys, so hopefully, like I said, we're going to finish lesson 1.2 today, I hope. I don't think we need graphing calculator technology, but I have mine out just in case you don't remember what certain kinds of graphs look like, but I don't think you'll... Oh, you know what? You might need it just for basic calculations, just for number crunching. Any scientific will work, but I'm going to use my grapher. We're still talking about rates of change. Yesterday, I was talking about how... Well, yesterday we were specifically finding the average rates of change, and I was talking about how if the average rate of change is increasing, a graph is concave up, and if the average rate of change is decreasing, a graph is concave down. And we said that the average rate of change is the slope between 2 points that are on a curve. So if you connected 2 points on a curve, then you could say, well, you know, there's lots of different rates of change between these 2 points, but the average one is, well, whatever the average rate of change is. And I mentioned, I think that was this period, the possibility of finding the rate of change at a single point using calculus. Well, we are going to be using context clues and a lot of number crunching to estimate what we call an instantaneous rate of change. And an instantaneous rate of change is literally the rate of change at a single point rather than 2 points, okay? And the way we do that is by getting closer and closer and closer using 2 coordinates to the actual single point we're working with. So we can use the average rate of change and just let the distance between the 2 points get smaller and smaller and smaller and smaller. And if you let it get small enough, you'll have a pretty accurate representation of what the slope, the rate of change would have been at a single point. Okay. So suppose an object is launched upward from a height of 120 feet with initial velocity of 48 feet per second, then this is the equation that models the height over time in seconds. It says find the average rate of change in the height of the object over these time intervals, and make sure that you include measurements. So what did we do? So first we're going to go from time equals 1 to time equals 1.1. Then we're going to go to time equals 1 to time equals 1.01. So you see we got closer to 1. And then look, 1.001, getting even closer to 1. This one, instead of adding another 0, what we did was we went down 0.001 and up 0.001. And notice that the number x equals 1, well t, excuse me, equals 1 is directly between these two. Because once we have these numbers down here, we're going to use that knowledge to estimate the instantaneous rate of change at exactly time equals 1. So I will be using the calculator for these decimal approximations. Cool? So there's really not a whole lot of math to be shown on the paper. Just know that I'm going to do, what color do I want to use? I'm going to be using average rate of change, so the change in the y's over the change in the x's. The change in the x's here is 0.1. The change in the x's here is 0.001. This one's 0.01. This one's 0.001. And this one is 0.002 because up 0.001, down 0.001. But that's what we're going to do. And I don't want to show all the calculations. I just want to write the average rates of change for each one. Okay? Well, the fraction. So first thing I'm going to do is I'm going to substitute 1.1 into this equation. Negative 16. Make sure you use the negative button, not the minus sign. Negative 16 parentheses 1.1 parentheses squared. Squared button is right there. Don't be afraid to use your parentheses. It's easier and faster than doing times. So I did negative 16, open parentheses, 1.1, close parentheses squared. Then I have to do plus 48, and I'm going to use parentheses again. Remember, I told you should be using parentheses every time you're doing a substitution. Plus 120. That's y2. 153.44. And y1 is what you get when you substitute in 1. So just negative 16 plus 48 plus 120, because the x's are just 1s now. So there's y1, 152. x2 minus x1 is 0.1. 153.44 minus 152 is, divided by 0.1 is 14.4. We need units. This is feet per second. There you go, feet per second. We're going to do the exact same thing, only now instead of substituting in 1.1, we're going to substitute in 1.01. Negative 16, 1.01 quantity squared. I love that squared button. Plus 48 times 1.01 plus 120. 152.1584. Now I know that AP says round to 3 decimals, but because that decimal comes to an end and because I'm really trying to drive home a concept here, I'm going to write out all 4 decimals. One 52.1584 minus 152. Well, I'm going to run out of space, aren't I? Over 0.01. So subtract that 152 again, because that's what we get when we substitute t equals 1. And divided by 0.01 is 15.84. Feet per second. I think that I'm driving home the idea of what I'm doing. So for C, rather, because I'm running out of space, rather than write the arithmetic, I'm just going to write the average rate of change. This time I'm going to use 1.001. Again, subtracting what I get for t equals 1, which was 152. And this time when I divide, it's not 0.01, it's 0.001. 15.984. What does it look like we're getting close to for our average rate of change? Looks like we're getting pretty close to 16, doesn't it? Let's see what happens for this last one. Now for this one, I'm not going to be subtracting 152. I am going to have to substitute in the 0.999. But I don't know if you know this, but one of the great things about scientific calculators and graphing calculators especially is, you see, I've already plugged in this 1.001. You see that? I don't have to do that again. I already know that the result for that is right here. So what I'm going to do is I'm going to use my up arrow until that's highlighted. And I'm going to hit enter. And that's essentially a copy-paste function. So I don't have to enter that 1.001 again. Pretty neat, huh? Now, actually, you know what? Let me plug in the 0.999, and then I'll show you how to do the whole copy-paste thing like I just did, okay? So let's negative 16, substitute in 0.999. Quantity squared plus 48 times 0.999 plus 120. There is x1. So here's how we're going to do this. x2, enter, minus x1, enter. So it copy pasted for me. Then I just hit, give me that number. And then I'm going to divide by the distance between these two numbers, which is not 0.001, but 0.002. Holy cow. Smack on 16. So what happened? What happened was we went immediately to the left of 1 and immediately to the right of 1 and found the average rate of change between these 2 points. But these 2 points are so close together that their average rate of change can be used to estimate the instantaneous rate of change at the point that's immediately between them. So using these rates above, what is your estimate for the instantaneous rate of change? Obviously 16. red. At t equals 1, rate of change of height is 16 feet per second. You know, all those times I was writing little s, I'm not sure if you can get away with little s or it has to be SEC. You know what, let's just make it SEC. Oh crap, I forgot to do that here. There. And usually the 3 decimals, 0.001 up and 0.001 down, that'll be enough for you to estimate an average rate, or excuse me, an instantaneous rate of change. So if I ask you to do it at the number 5, at x equals 5, I would expect you to substitute in 5.001 and 4.999, and then find the average rate of change between those 2 points. Cool with that idea? So 0.001 up, 0.001 down, average rate of change, that'll get you pretty darn close to the actual answer. By the way, the actual answer is 16. Using calculus, it would be right on 16. None of this average stuff. Questions, comments, concerns, or are you okay with that? Why did you do the first 30 if you don't need to do that? Because I was getting you to see that we were heading towards the number 16. Because if I had just said, hey, this works, then you'd have been having to take my word for it, rather than see it as I got closer and closer to the point, seeing it run into the number 16. This is called a limit in calculus. The limit is approaching 16. And now I was able to ask right here, make a prediction, what do we think it's heading towards? Basically everybody said 16, and then this confirmed we were headed there. So yeah, that's why. So if I ask you to do it on a test, you don't need to do all of these. Just get really close at the very first step, because now you know it works. So in the AP Precalculus course, we cannot find exact rates of change of a function at a single point. You'll be able to do that next year in calculus. It's actually pretty easy. Our techniques will be to recognize that the instantaneous rate of change is the slope of the graph at a single point. Remember, it's an estimate, but it's really accurate. We can do this. We can do one of these. We can estimate the rate of change at a point by using average rates of change over really small intervals. Or the other way of doing it is by using 2 points on what we call a tangent line. Anybody remember what a tangent line is from geometry? It's okay if you don't. A tangent line is a line that gets that touches a shape without going through it. Remember tangent to a circle? Let me draw a shape real quick just so you can see. Like if I gave you a quadratic, then a tangent line would be something like this. It touches the shape without going through it. That's a tangent line. So if I knew the slope of this red line using 2 of its points, then the slope of that line could be used to estimate the instantaneous rate of change of the blue parabola where they touched each other. So that's a tangent line. For each of the following functions, describe the average rate of change over the given interval as positive or negative, and try to do that without actually substituting in numbers. The way you do that is by having an idea of what that graph looks like. And if you're not sure what a graph looks like, grab your graphing technology. Turn it on, clear my screen. Hopefully everybody in the room knows what x squared looks like. But right here at the top, you have a y equals button. That takes you to a list of 10 functions that you could type in. We're going to type in x squared. This is the button that you're going to use for variables. Depending on the mode of the calculator, it will use a different letter. Right now we are in function mode, so it's going to use x. Squared is right there. Every other exponent, you would use the caret symbol, but squared. This button right here will graph the image for you. If you've never graphed anything before on this calculator, it will default to 10 in all 4 directions. So that's what I'm seeing, 10 and negative 10, 10 and negative 10. So hopefully, we all know that this graph looks like this. And the numbers x equals 2 and x equals 3 are on the right side. So my tangent line would look like this, between 2 and 3. Or if I wanted to connect the dots at x equals 2 and x equals 3. I'm just drawing the tangent line. Is that average rate of change positive or negative? It's positive. Yeah. The slope of that tangent line that I just drew is positive. And that's without actually plugging in numbers. So I haven't had to actually do the average rate of change. Log of x. You know what? Well, I'll just go back to y equals, clear out x squared. Your log button on this calculator is right here. Log. Now on the screen, it opened a set of parentheses, and that's waiting for the argument. That's where your variable x goes. Please be in the habit of closing those parentheses. Okay? And hit graph. Does the logarithm, from algebra 2, does the logarithm graph have an endpoint? No, it does not. That screen makes it look like it does, doesn't it? The reason why is because the logarithm graph gets very vertical very fast. This calculator doesn't have a way of showing you that. So the moment it encounters something too steep to color 2 pixels side by side, like if they would have been within 1 pixel vertical, the calculator breaks and it stops graphing things. But if I were to zoom in, it would draw more. This is what the log graph looks like. It has a vertical asymptote at the x-axis. These are both positive x values. My tangent line then, if I were to connect these two x's, it wouldn't actually be tangent, but imagine I was drawing a tangent line at an x between those two, would look something like this. Is that a positive or negative average rate of change? Hopefully more than Barry can see that that red line has a positive slope. One over x squared, if you can remember back to our algebra 2 days, is exponential decay because the exponential base is between 0 and 1. So that's decay. It looks like this. Just look at this curve. This is an always decreasing function. So is the average rate of change going to be positive or negative? Lots of people, please. Negative. It's very clear that from here to here, I'm assuming I crossed that thing twice, that tangent line would have had a negative slope if it was tangent, or the average rate of change connecting those two. Either way, it's negative. This is an always decreasing function. And this is a negative x squared graph that's been shifted up 5. It looks like this. Well, we graphed quadratics in algebra 2, right? And it's x squared with the negative number on the front, so it points down. And then this is the transformation plus 5 at the end. It's just written out of order. Okay? Yeah, it's just written out of order. It should technically be read as this. So it has a negative leading coefficient. So its vertex has been shifted up 5, but it points down. And that will be, I'll go back to blue, I guess. So it's going to look like this. And it'll be symmetric around the y-axis. 1 and 4 are both positive x values, though. Negative average rate of change. If you can remember back to your basic functions that you learned in algebra 2, you should be able to talk about whether or not an average rate of change is positive or negative without the graphing technology. The tangent line concept, explained a little bit better. Here's a graph of f of x. A tangent line at f, a tangent line of f, there we go, wrong two-letter word, at the point x equals -3 is drawn on here. So I have a coordinate at -3, 3, and a tangent line, so that line touches the curve at -3, 3 without going through it. In calculus, you will be able to prove that the slope of this tangent line is the instantaneous rate of change at this point. Like I said, it's very easy to do. We, though, are going to use that tangent line to estimate the rate of change, simply by finding what the slope of that tangent line is. So find another pretty point on the tangent line and count your rise over run. If you go from here to here, we'll know the slope of that tangent line. Looks to me like it's rise 1, 2, 3, 4, run 1. I would estimate that average rate of change. Or did it not? Oh, you know what? That didn't hit the point -3, 3. It was close though, wasn't it? We don't have an actual value there because we don't have a function there. Do we have any exact pretty points? I mean, that one was exact, but that one wasn't. Do we have any exact pretty points? We really don't. Look, it didn't hit pretty there and it didn't hit pretty there. We're going to have to estimate that one. What y value do you want to call that? It's a little bit above 3. What do you guys want to call it?
2.
Well, it's not 3, so we can't call it 3, but maybe 3.2 or make the math easy. How about like 3.25 maybe? Okay, let's call it 3.25. So our average rate of change here is going to be f of -2 minus f of -3 over -3 minus -2. And we know we're going to get a positive slope. We can see that. It was almost 4, but that point wasn't perfect. Bless you. So we said this one's 7, and we're going to estimate that one at 3.25. -3 plus 2 is -1. Something went wrong. I know, hold on a second. What did I do wrong? Look at my order. -2, -3, -3, -2. I switched the order down here by accident. No. Which point is first, which point is second doesn't matter, but you can't mix and match. And I just mixed and matched by accident. And I knew it was wrong because I was about to get a negative slope. Anyway, phone call over. Yeah, sorry, I mixed and matched by accident. This should be +1. -2 plus 3 is +1. So what is this, 3.75? So almost 4. We can see it was almost 4. Okay? She's asking a question. What's the question back there?
What's the first thing for? Like the f negative.
This is me finding, this is y2 minus y1, x2 minus x1. F is the name of this function. And f of -2 means the y value when x is -2. So this y value. F of -3 means the y value when x is -3. So this y value. It's just a way of representing it. Remember yesterday with the cost function, how we did that? Those are just y values. It says sketch the tangent lines of f at the 3 points shown on the graph. Oh, yes, Barry? Shh. We have estimated the instantaneous rate of change at x equals -3 using the slope of that tangent line. Yes. Now, without knowing what the equation is for this polynomial, we wouldn't be able to tell you exactly what the instantaneous rate of change is, but that's a good estimate. Ian? Is that a question? Oh, okay. All right. Next, it says sketch more tangent lines, and then we're going to describe the behavior of the graph and the relationship of the rate of change at x equals 2. That's right here. So let's sketch some more tangent lines, and we don't need to be perfect. Let's do. I'm going to turn the paper because I'm not good at drawing lines unless they're like straight up and down. But this, if I were to draw a line, let's see, like that. There we go. There's a good tangent line. That's pretty decent. Now, we don't have to estimate the slope there or anything like that. Here's the tangent line at 2, -3. And the last one, and I'll do in green, a tangent line here. That one's going to be really steep. Let's see, do our best. Oh, go home, green line, you're drunk. Sorry. There we go. There we go. I did my best. So, 7C. It says describe the behavior of the graph and the relationship of the rate of change at x equals 2. Okay, I tell you what. This red line, does it have a positive slope or a negative slope? Negative slope. The green line, does it have a positive slope or a negative slope? Positive. Okay, so we know to the left of this number from previous knowledge, this graph was decreasing, right? So this is a decreasing graph, but it's concave up. And over here, it's increasing and concave up. These negative slopes are obviously smaller than 0 because they're negative. This positive slope is greater than 0, so positive. Then what do we think is going on right here? What do you think the slope of the curve is at this point? It's got to be 0, right? Because on this side it was negative and on this side it was positive. The only way you go between negative and positive is if you pass through 0. So we can say that the graph of f changes from decreasing to increasing at this point, and this point then would have a rate of change of 0. It is considered a constant point, not a constant section. There is no interval there because it's happening at a single instant in time. But yes, it's considered a constant point. We call it a, hold on now, what's the word I'm looking for? Oh, we use it in IB. What's it called when you're holding still? Looking for one word that means standing still, like holding still. Huh? No. I mean, you're not wrong. I'm just looking for stationary. There we go. Stationary. I knew it started with an S when he said stagnant. Stationary. It's called a stationary point in calculus because it's considered not decreasing, not increasing, so it clearly is stationary. But you don't need to know that for this course. Okay. Describe the behavior. We said f of x is decreasing until x equals 2 and increasing after x equals 2. So rate of change equals 0 at x equals 2. Okay. Stationary point. It's also called a turning point. Again, you don't need to know that yet, but we call it a turning point because we changed behavior. We stopped decreasing, started increasing. So anytime increasing, decreasing behavior changes, we call that place where it happens a turning point. All right, so summary of behavior: positive, negative, increasing, decreasing. But specifically when talking about the rate of change. So if the rate of change is positive, what is your graph doing? So when your rate of change is positive, what's your graph doing? It's going up. Well, you don't know, you just know it's going up. So if rate of change is positive, your graph is increasing.
So it's just concave up?
That's a different idea. It's just increasing. It's going up. See, look, this is going up and this is going up. So it doesn't have anything to do with concavity. If the rate of change is negative, then your graph is, lots of people, come on, decreasing. What if your rate of change itself is increasing? What's positive? The rate of change of the rate of change. But what does that mean? If the rate of change is getting larger, what does it tell you about the graph? Increasing just means that the rate of change is a positive number. But if it's positive and getting larger, we talked about it yesterday. Concavity. What do we know about the concavity? It's concave up. So that's concave up. And if the rate of change is decreasing, concave down. So look at this curve here. If I had to estimate where the inflection point is, I would say that it's halfway between x equals -2, because that's a flat point, and x equals +2, because that's a flat point, and halfway between x equals 2 and x equals -2 is this one right here. So I would actually estimate that this thing changes concavity at the y-axis. It is increasing and concave down, decreasing and concave down, decreasing concave up, increasing concave up. Yes?
When you're trying to figure out like when something goes from concave up or to concave down,
When concavity changes, yeah?
does it have to be like a specific like point?
So concavity will always change at an inflection point for an unbroken curve. So if it's a polynomial, which is what this would be, then a point of inflection will always happen at a point somewhere between a maximum and a minimum. At this point in the game, the best we could do is find the average between the two x's. With calculus, you'll be able to find out where it actually is. As long as it's an unbroken curve. Okay? But I mean, there are times when you have broken curves, like this one. This is the equation 1 over x. This one doesn't have an inflection point, but it does change concavity. This side's concave down, this side is concave up. But because those two pieces don't touch each other, there is no inflection point. So I wanted to say it's only a point if it's an unbroken curve. Call it a smooth curve. Be careful and watch the words. You must be comfortable reading the words. You need to be sure. Is a question asking you about the graph you have? Or is a question asking you about the rates of change of the graph you have? These are two completely different concepts. The graph of G is shown at the right. Complete the statement below to describe the graph of G and the rate of change of G. The graph of G, is this increasing or decreasing? Increasing. I'm just going to circle because it's faster. What about its concavity? It is concave up. I agree. The reason why is because the rate of change of G is positive, which is what makes it increasing. And what makes it concave up is because the rate of change is increasing. All right? Balls! You all said positive, and I circled negative like a ding-a-ling. I think I even said positive. I don't know why I circled negative. I know, I don't, brain fog. Sorry, wrong circle. Can I flip the page without anybody panicking? Yes. Okay, nobody's panicking. Is that the last of it? Yes, it is. Here we go. It says, describe the graph and the rate of change. So, increasing or decreasing? Decreasing. Then what is the rate of change, and what is the rate of change doing for this one? Well, let me ask you this. Is this concave up or down? If it's concave up then what is the rate of change doing? So what's happening to our brains? Well, let's look. Imagine your tangent lines. If I drew a tangent line, can we agree that the slope here would be like -2? -1? -1/2? You see how those numbers are getting larger? So that rate of change is increasing. This one, is this increasing or decreasing? Come on, people, classroom, not Barry. Increasing. Then, since it's increasing, well, not since it's increasing. I know it's increasing, but what is the rate of change doing? And base your fact upon the concavity. Decreasing. This is concave down. Therefore, the rate of change is decreasing. Look. Slope of like 3. Slope of 2. Slope of 1. Slope of 1/2. They're clearly getting smaller.
I have a question.
Yes, Barry?
Is there such thing as concave left and right?
There is not concave left and right. Because those would... No. So, but let me draw it. Let's say the graph looks like this. Like shooting star. That's still concave down. Because everything goes from left to right. It's concave down, look. Okay. Shh, we're not done yet. The traffic flow at a particular intersection is modeled by this function. Eek! Trigonometry! I know, uh-oh, lots of voices. Shh. It says, what is the average rate of change of the traffic flow over this time interval? So that just means find the average rate of change between this time and this time. That means we need to actually plug these in. So I'm going to grab a handy-dandy calculator. We're using 3 and 8. Second quit. Actually, let me clear that out for next period. 96 plus 5 sine of 8 over 2. That's 4. And 96 plus 5 sine of 3 over 2.
That just says 6 plus 5 sine of 3.
Oh, I missed the 9? Okay, if you ever miss a character like I just missed the 9, you don't have to clear it all. Hit second, and then delete button will let you insert a character. There. Thank you, Barry. So second insert. There's your insert command right there. It's so you don't have to retype it all. I put 8 in it once, and I put 3 in it once, because I needed to know the y values. Now I'm going to find my average rate of change. Y2. Three decimals minus Y1. 3 decimals over Y2, or it's going to be X2 minus X1. And I'm not trying to actually subtract those numbers, so what I'm going to do is I'm going to do that number minus that number. I'm just hitting enter to copy paste. Hit enter there. And divide that by 5. There is your average rate of change. To 3 decimals, negative 1.754. And this was traffic flow. Indicate the units of measure. So this would be what number of cars per minute?
Negative cars?
Yeah. So what does that rate tell you about the flow of traffic during that time? It's decreasing. It means the number of cars traveling through that intersection is decreasing during that time. Yeah, negative cars, no. Yeah, number of cars is decreasing. Because the rate of change there is negative, clearly our graph is decreasing there. This is number of cars is decreasing by, I don't know, about 1.754 cars per minute. Cars per minute. Yeah, because I forgot the R. Is it possible to find the rate of change at a specific time? Hey, guys, is it possible to find the rate of change at a specific time? Yes, you can estimate it over if you use a very small window of time. Can be estimated on a small window of time.
Would it be instantaneous?
That is at a single, yes. But it can be estimated over a small interval. The reason why we can't use this average rate of change idea for instantaneous is because it would make us divide by 0 because the two times would be equal. Well, we didn't get to C and D, but I think we pretty much beat this horse to death. I think we're ready to go.